This hybrid device can be obtained by merging the chemistry of both of them. If we take certain material from the battery side and another material, if we take another material from the supercapacitor side and then merge them or combine them, then we get a new device called supercapatery or supercapacitor. It has the combined feature of both of them, battery as well as supercapacitor. Basically, supercapacitor is quite different as that of conventional ordinary capacitor. It is an electrochemical device which stores energy through polarized electrolytic solution. In a similar fashion, battery is also an electrochemical device which store energy on the end of Faradic reaction, chemical reaction. In case of supercapacitor, no Faradic reactions are involved. Although there is a one type of supercapacitor in which a partial redox reaction are there, which will be explained in the coming slide. But in case of battery, a small redox reaction or chemical reaction, oxidation reduction reaction is always there. Supercapacitor is categorized into two categories: EDLC, electric double layer supercapacitor, and supercapacitor. The electrode material, which is generally made up of electric double layer supercapacitor, is taken from activated carbon, which is being extracted from the biomass, vegetable waste or food waste. And second is carbon nanotube or graphene. As far as the charge storage mechanism is concerned, in case of electric double layer supercapacitor, the charges are stored due to electrostatic attraction because of absorption and desorption of ion on the electrode surface. And there is a double layer is formed at the interface of the electrode and the electrolyte. That is why it is called electric double layer supercapacitor. One of the distinguished thing is that the electrode material which is formed by electric double layer supercapacitor is activated carbon because it shows a good conducting nature. And if we discuss about supercapacitor, the electrode material which is generally made from supercapacitor is organic polymers or metal oxide, nickel oxide, iron oxide, manganese oxide, etc. And as far as the charge storage mechanism is concerned, so in case of supercapacitor, a partial redox reaction takes place at the surface of the electrode and electrolytes. So this is the property of the battery. In case of battery, 100% redox reactions are there, but here a partial redox reaction. So there exists a certain property in case of supercapacitor, which is taken from battery or rechargeable battery. What is the motivation behind this research work? As in the previous slide, I have discussed that battery has high energy density but low power density. On the other hand, the supercapacitor has high power density but low energy density. And if we merge these two material, one from the battery side and another from the supercapacitor side, we get the hybrid device called supercapatery or supercapatery, and now they exhibit these three properties: high energy density, high power density, and also possesses high stability. As far as the stability is concerned, we will discuss in the coming slide. Look at the Reagan plot of energy, specific energy and specific power. This plot is taken for various energy storage devices. The red curve, which is taken from redox flow battery and fuel cell. This curve clearly indicates that all redox flow battery and fuel cell possesses high specific energy density, energy stored per unit mass, but they possesses low power density, just like at the bottom on the y-axis. Because on the y-axis we take in we take specific
Specific
power,
power.
but on x-axis we take specific
Specific
energy.
energy.
And if we consider this pinkish curve, it is taken from electric double-layer supercapacitor. It has low energy density, but meanwhile it possesses high power density. Is it clear?
Yes, sir.
And our hybrid device, supercap battery, look at this bluish curve, which exhibit which shows which act as a bridge between redox flow battery as well as electric double-layer supercapacitor, because its property lies intermediate between battery and supercapacitor. It has a good energy density as well as it has an excellent power density. So our motivation is to fabricate such a device which exhibit the combined feature of both battery and supercapacitor. This is one of the main objectives which we have to achieve, which I have to achieve during this talk. Although during this research we have done this, we have fabricated this device, but we will explain how to fabricate this device. In this particular slide, in case of as far as capacitor nature electrode material is concerned, as I have mentioned that in case of supercapacitor, the charge storage mechanism takes place because of electrostatic protection, and the material which is taken for the electrode material is generally made up of carbon material. It has high cyclic stability, high power density, works on wider potential window, and but there is a
low
deficiency
energy
of
low
low
energy
energy density. On the right side, if we consider the battery grade material, here the charge storage mechanism takes place periodically, redox reaction, oxidation reduction reaction, and the most famous material for the electrode fabrication is metal oxide, metal phosphate, organic polymer, etc. It has high capacitance, high energy density, works on the small potential window. Supercapacitor works on the wider potential window, but it works on the small potential window, but there is a deficiency of low power density. And these are the properties of our hybrid device, which is taken from by merging the chemistry of these two. High power density, high energy density, wider potential window, and showing excellent cyclic stability. If we consider the graphical analysis of all these three devices, one is battery, second one is supercapacitor, and third one is our hybrid device, supercapacitor. Look at the first curve. This is the cyclovoltammetric curve of supercapacitor between current and voltage. In case of supercapacitor, when the electrode is being charged, the first red curve shows the charging of the electrodes, and the bottom blue curve shows the discharging of the electrodes. So it almost in rectangular shape for one complete cycle. इसमें थोड़ा सा हम पाते हैं कि कंप्यूटर की वजह से रेक्टेंगुलर शेप आ गई है। जब ये सुपरकैपेसिटर चार्ज हो रहा है, इसकी चार्जिंग जो है इस तरह होती है कि ये इस तरह जाएगा, वन मीन्स आप साइकिल करेंगे, और फिर ये जब डिस्चार्ज होगा तो ये वापस इस तरह तो ये computer presentation में आ गया। तो any of the almost the rectangular shape of the supercapacitor curve shows the charging and discharging behavior of the electrode material. And if we consider the charging discharging or cyclovoltammetric curve of pure battery grade material, there is slightly hump appears, which indicates the redox reaction, oxidation reduction reaction at the electrode surface and electrolytes. A slightly hump is appeared. It would mean that during charging process or ion transportation, a certain chemical reactions are involved which were not available in case of supercapacitor. And when we merge these two and we fabricate a hybrid device, look at the middle figure. It shows the combined chemistry of both of them. It has a rectangular shape, a slightly hump is because of redox reaction. It would mean that the supercapatery device exhibits the combined feature as well as their CV curve is concerned. Is it clear?
Yes, sir.
सुपर में रेक्टेंगुलर शेप है, बैटरी में स्लाइटली हम्स आ रही है, ऑक्सीडेशन प्रोसेस के दौरान भी केमिकल रिएक्शन हो रहा है और रिडक्शन में भी केमिकल रिएक्शन हो रहा है। अब जब हमने सुपर कैपेसिटी बनाई है तो इसमें बैटरी का कंट्रीब्यूशन भी है और सुपर कैपेसिटर का कंट्रीब्यूशन भी है, तो फिर इसकी कर्व को देखें स्लाइटली हम नजर आ रहा है, ये हम वो बैटरी ग्रेड वाला जो इलेक्ट्रोड है उसका कंट्रीब्यूशन है और जो रेक्टेंगुलर शेप है वो कैपेसिटर की वजह से है। तो नीचे आगे these are the schematic representation of hybrid device. One electrode is activated carbon and other electrode is, this is our synthesized fabricated electrode, which we will explain in the coming slide, and there is a electrolyte solution between them. There is no electrolyte exists in case of conventional capacitor. One thing you should keep in mind, electrochemical supercapacitor possesses quite different nature and properties as compared to conventional capacitors, ordinary capacitors. And objective of this research work. The first aim is that optimization of synthesis rule for the synthesis of electrode material, developing a suitable electrode material for energy storage application. There are variety of electrode material which can be synthesized for the fabrication of hybrid devices. So our aim to develop a suitable electrode material for energy storage application, and then fabrication of supercapatery device which showing high power density, high energy density, good cyclic stability, no degradation of energy takes place with passage of time. These are the some distinguishable properties possessed by our hybrid device called supercapacitor, which I have explained in the previous slide. What are the electrode material which can be utilized for the synthesis process or fabrication of a hybrid device? A number of people have worked on different materials and their results have been published. If we discuss metal oxide like iron oxide, nickel oxide, manganese oxide, our metal oxide possesses small electrochemical properties. Small electrochemical properties mean that in case of metal oxide, the phenomena of chemical reaction, redox reaction, oxidation reaction could not take place as in case of metal phosphate and sulfide. It would mean that कि केमिकल रिएक्शन प्रोसेस जो है ऑक्सीडेशन रिडक्शन का वो मेटल ऑक्साइड के अंदर बहुत कम पाया जाता है. They degrade rapidly. If we fabricate a device which is made up of those electrode material which is taken from the metal oxide, and we charge and discharge that electrode for a number of cycles, 2000 cycles, 3000 cycles, 5000 cycles, the material degrades rapidly with passage of time. That is why it is not the best choice for the electrode fabrication. Similarly, their capacity decreases rapidly. When the certain amount of charge is being deposited on the electrode surface, we know that each electrode has certain capacity. There is an ability to store charges. Amount of charge stored per unit mass is called capacity. This term is little bit different as you have studied in your basic classes like FSC or DS level, where you define supercapacity, ability of a capacitor to store charge. But in this research work, we take capacity, amount of charge stored per unit mass. So when we it has low conductivity and stability. Again, the same problem like in case of metal sulfide as does in metal oxide. Low conductivity and low stability, but good redox activity. When we discuss metal sulfide, it's a chemical reaction in case of metal sulfide
occur in a much more better rate as compared to metal oxide. But low conductivity and low stability put a question mark on their utilization as far as electrode fabrication is concerned. The third category is that of metal phosphate, which shows intermediate conductivity, rapid ion transport mechanism, better stability, but low redox active nature. When we discuss metal phosphate, all these three properties exhibited by the metal phosphate, but as far as the chemical reaction is concerned, it has low redox active nature. The fourth category is conducting polymers, which show excellent conductivity, low, high redox active nature, and as well as it shows excellent stability. अब जो मेटल फास्फेट के अंदर मेटल फास्फेट के अंदर लो रिडॉक्स एक्टिव नेचर है, यानी इसकी केमिकल रिएक्शन बहुत स्लो होती है, लेकिन कंडक्टिंग पॉलीमर्स जो हैं इनका रिडॉक्स एक्टिव नेचर बहुत ज़्यादा है। जैसे पॉलीएनिलीन है, पॉलीएनिलीन एक ऑर्गेनिक पॉलीमर है, तो ये जो डेफिशिएंसी है मेटल फास्फेट की, इसको ओवरकम किया जा सकता है अगर हम कंडक्टिंग पॉलीमर्स को एज ए इम्प्योरिटीज मेटल फास्फेट के अंदर डाल दें। मेटल फास्फेट इसलिए चूज किया जा रहा है, द मोस्ट रिपोर्टेड एलिमेंट इन द रीसेंट टाइम फॉर द इलेक्ट्रोड पब्लिकेशन इज दैट ऑफ metal phosphate, in which cobalt phosphate play a promising role due to these distinguishable properties. So, for the electrode fabrication and synthesis, I have considered cobalt phosphate and their composites. Chosen the application is cobalt phosphate and its composite. Different methodology has been developed for the synthesis of the electrode material, like sol-gel technique, hydrothermal technique, but I have worked on sonochemical method, sonochemical synthesis technique. Because of certain distinguishable features, this sonochemical synthesis technique has been developed or have been preferred over all other techniques, because by using this technique one can grow a particle in a much faster rate. The size of the particle is almost uniform by using this technique. We can vary the amplitude energy of the ultrasonic wave, because in case of sonochemical there is a probe sonicator in which ultrasonic waves are emitted out, which is attached with a certain generator or a certain source from which ultrasonic waves are emitted out, and we place a solution inside the beaker under this probe sonicator in which chemical reaction takes place, which will be explained in the coming slide. These are the characterization techniques, measurements. First of all, X-ray diffraction spectroscopy. As you all know that by using these techniques, one can easily identify the internal structure of the material, crystal grains, interatomic spacing, interplanar spacing, microstructure of the material, internal structure. And if we consider scanning electron microscopy, this is limited for the surface study. Surface morphology can easily explain by using scanning electron microscopy, while internal structure or internal microstructure can easily be explained by using X-ray diffraction. And then cyclic voltammetry and galvanostatic charge discharge. These are called electrochemical measurements, electrochemical characterization techniques, which we have focused in this research work. Electrochemical impedance spectroscopy, in which different frequencies is allowed to fall on the material, and we check its impedance. When charges are fine transports to electrolyte, how much resistance they offered by the electrolyte for the transportation of ions or the transportation of charges. And then we apply theoretical modeling on the device data, real device data.
So first of all, we synthesize our precursor material, host material, cobalt phosphate. How we synthesize this cobalt phosphate in the lab? First of all, we take 0.05 molar solution of cobalt chloride in deionized water, and then place it in a beaker under probe solitator.